I need to tell you something that will contradict everything you learned in school. Magnetism does not exist. Not as a separate force. Not as an independent phenomenon. The magnetic field you learned about, the one that makes compasses point north, that holds magnets to your refrigerator, that powers electric motors, is not real in the way you think it is. It is an illusion. A relativistic illusion created by your motion relative to electric charges. This is not philosophy. This is not semantics. This is physics. And I can prove it to you with nothing more than special relativity and Coulomb's law. What you call magnetism is electricity viewed from a different reference frame. Let me show you how this works. The mystery of the magnet. Pick up two magnets. Hold them close together. They either attract or repel depending on orientation. Why? The standard explanation involves magnetic fields. North poles attract south poles. Field lines flow from north to south. The magnets interact through their fields. But this explanation hides something fundamental. It treats magnetism as a primitive force, something that simply exists, irreducible, unexplained. In 1864, James Clerk Maxwell published equations unifying electricity and magnetism. His equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. Light itself is an electromagnetic wave, oscillating electric and magnetic fields propagating through space. Maxwell's equations were a triumph, but they raised a question that took 40 years to answer. Why are electricity and magnetism connected? What is the deeper relationship? Einstein answered this question in 1905. The answer changed everything. The wire and the charge. Consider the simplest electromagnetic system. A straight wire carrying electric current. Inside the wire, electrons are moving. In a typical copper wire carrying 1 ampere, the electrons drift at approximately 0.1 millimeters per second, extremely slow. Now place a positive test charge outside the wire, stationary relative to the wire. The wire is electrically neutral. It contains equal numbers of positive charges, copper nuclei, and negative charges, conduction electrons. The positive test charge should feel no electric force. The attractions and repulsions cancel. And indeed, in the laboratory frame, the test charge feels no electric force. But it does feel a force, a magnetic force. The moving electrons create a magnetic field that circles the wire. The stationary test charge sits in this magnetic field, but does not move through it. So classical electromagnetic theory says it should feel no magnetic force either. Wait, that contradicts experiment. A current-carrying wire does exert a force on nearby charges. Let me resolve this apparent contradiction by changing reference frames. The electron's perspective. Jump to the reference frame of the moving electrons. In this frame, the electrons are stationary. The positive nuclei of the copper wire are moving backward. In the opposite direction, the electrons were moving in the laboratory frame. Now here is where relativity enters. Moving objects contract in the direction of motion. This is length contraction, a direct consequence of special relativity. In the electron's reference frame, the positive nuclei are moving. Therefore, the spacing between nuclei is contracted. More positive charges per unit length. The electrons are stationary in this frame. Their spacing is not contracted. Same number of negative charges per unit length as in their rest frame. The wire is no longer electrically neutral. In the electron's reference frame, the wire has a net positive charge density. Positive charges are compressed. Negative charges are not. This net positive charge creates an electric field pointing radially outward from the wire. The test charge, which is also moving in the electron's reference frame, sits in this electric field. It feels an electric force. Calculate that force. Transform it back to the laboratory frame. It exactly equals what we call the magnetic force. Magnetism is electricity in disguise. This is the key insight. What we call magnetism is the relativistic correction to electrostatics when charges are in relative motion. There is no magnetic field as an independent entity. There is only the electric field, viewed from different reference frames. When you move relative to charges, length contraction changes the apparent charge density. This creates electric fields that would not exist if you were stationary relative to those charges. We call these motion-dependent electric fields magnetic fields, but they are not a separate force. They are how electricity looks when you account for relativity. The mathematics. Let me make this precise. Consider a wire with linear charge density lambda 0 of positive charges, nuclei, and linear charge density minus lambda 0 of negative charges, electrons. The wire is neutral. Net charge density is 0. Now the electrons move with drift velocity v. In the laboratory frame, length contraction affects the electron spacing. Lambda space equals minus lambda 0 times gamma, where gamma is equals 1 over root of 1 minus v squared over c squared is the Lorentz factor. But the electrons were originally spaced at their rest frame density. When they move, their spacing contracts. So the moving electron density becomes lambda space equals minus lambda 0 times gamma. The nuclei remain stationary, so their density stays lambda 0. Net charge density, lambda 0 minus lambda 0 gamma equals lambda 0, 1 minus gamma. For small velocities, gamma is approximately 1 plus v squared over 2c squared. So, net charge density is approximately minus lambda 0 v squared over 2c squared. This is extremely small. Electron drift velocities are tiny, about 10 to minus 4 meters per second. The ratio, v squared over c squared, is about 10 to minus squared 5. But the number of electrons in a wire is enormous, approximately 10 to squared over 3 per centimeter. The tiny relativistic correction, multiplied by enormous numbers, produces measurable forces. This is magnetism. Why magnets attract? Now consider permanent magnets. No current flows through them. No electrons drift along a wire. How does relativity explain their magnetic behavior? The answer involves electron spin. Every electron has an intrinsic angular momentum called spin. This spin creates a magnetic moment. The electron behaves as a tiny magnet. But wait, if magnetism is just relativistic electricity, what is electron spin really? Electron spin is a relativistic phenomenon. When Paul Dirac derived the equation for relativistic quantum mechanics in 1928, spin emerged emerged automatically. It was not added by hand. It appeared because the equation had to be consistent with special relativity. The electron's magnetic moment comes from the coupling between its spin and the electromagnetic field. This coupling is inherently relativistic. In a permanent magnet, the electron spins are aligned. Trillions of tiny magnetic moments point in the same direction. Each electron's magnetic moment arises from relativistic effects. The macroscopic magnetism of the bar magnet is the sum of these relativistic contributions. When two magnets interact, their aligned electron spins create fields that exert forces on each other. These forces are ultimately relativistic corrections to the electromagnetic interaction between the electrons. The Lorentz transformation of fields. Maxwell's equations describe how electric and magnetic fields relate to charges and currents. But they do not explain why electricity and magnetism are connected. Special relativity provides the explanation. Electric and magnetic fields are components of a single entity, the electromagnetic field tensor. When you change reference frames, electric and magnetic fields mix together. The transformation equations. E and the prime equals E and the prime. E prime equals gamma E and the prime plus V times B. B prime equals B and the prime. B prime equals gamma B and the prime minus V times E slash C squared, where the prime means parallel to the direction of motion, and the prime means perpendicular. Look at the second equation. In a frame where E and the prime equals 0, no perpendicular electric field, a moving observer sees E prime equals gamma V times B. An observer moving through a magnetic field sees an electric field. The magnetic field has transformed into an electric field. Similarly, look at the fourth equation. In a frame where B and the prime equals 0, no perpendicular magnetic field, a moving observer sees B prime equals minus gamma V times E slash C squared. An observer moving through an electric field sees a magnetic field. Electric and magnetic fields are the same thing, viewed from different reference frames. The current carrying wires. Two parallel wires carrying current in the same direction attract each other. This is the basis of the definition of the ampere. The standard explanation: each wire creates a magnetic field. The other wire's current experiences a force in that field. The relativistic explanation. In the reference frame of the electrons in wire 1, the electrons in wire 2 are moving at a different velocity. Length contraction affects them differently. The charge densities seen from each electron's perspective are not zero. Net electric fields appear. These fields exert forces. Calculate the force using only electrostatics and length contraction. The result matches the magnetic force exactly. You do not need the concept of magnetic field. You need only Coulomb's law and special relativity. Why does this matter, you might ask? If we can calculate everything using either approach, why does it matter whether magnetism really exists? Because it reveals something profound about the structure of reality. The universe does not contain two separate forces, electricity and magnetism. It contains one force, electromagnetism, that appears different depending on your motion. This is the principle that led Einstein to special relativity in the first place. In his 1905 paper, Einstein began with an apparent asymmetry in electromagnetic theory. A magnet moving past a conductor versus a conductor moving past a magnet. The observable results were identical, but the theoretical explanations seemed different. Einstein realized this asymmetry was an artifact of incorrect assumptions about space and time. Once you accept that the speed of light is constant and that space and time transform together, the asymmetry vanishes. Magnetism is not a force. It is a perspective. The deeper unification, this unification goes further. In quantum electrodynamics, the quantum theory of electromagnetic interactions, the photon mediates all electromagnetic forces. The same particle, the same interaction, whether you call it electric or magnetic. The electromagnetic force is one of 4 fundamental forces in the standard model of particle physics. But even among these 4, there are deeper connections. The electromagnetic force and the weak nuclear force are unified at high energies into the electro-weak force. This was demonstrated in the 1970s and confirmed by experiment. The pattern repeats. Forces that appear separate at low energies are revealed as aspects of a single force at higher energies. Magnetism's illusory independence from electricity was the first clue to this pattern. The unification achieved by special relativity pointed the way to deeper unifications. Practical implications. Understanding that magnetism is relativistic electricity has practical consequences. Electric motors and generators convert between electrical and mechanical energy using magnetic fields. But those magnetic fields are created by moving charges. The relativistic perspective explains why the design principles work. Transformers transfer electrical energy between circuits using changing magnetic fields. But changing magnetic fields are really changing configurations of electric charges. The energy transfer is fundamentally electrical. Magnetic resonance imaging, MRI, uses strong magnetic fields to align nuclear spins. But those nuclear spins are themselves relativistic phenomena, and the magnetic interactions are relativistic corrections to electromagnetic forces. The illusion is useful. We continue to speak of magnetic fields because the mathematics is convenient, but the underlying physics is unified. The field concept. Michael Faraday introduced the concept of field lines in the 19th century. He imagined lines of force spreading through space, connecting sources to the places where forces are felt. Maxwell mathematized Faraday's intuition. The electromagnetic field became a real physical entity, carrying energy and momentum, propagating as waves. Special relativity showed that electric and magnetic fields are not separate entities, but components of a single field tensor. The field remains real, but its decomposition into electric and magnetic parts depends on your motion. In your rest frame, a stationary charge creates a pure electric field. In a moving frame, that same charge appears to create both electric and magnetic fields. The total electromagnetic field is frame independent. Its decomposition into E and B is frame dependent. This is analogous to how energy and momentum combine in relativity. Neither energy nor momentum alone is conserved in all frames, but the four-momentum, combining energy and momentum into a single four-dimensional vector, is frame independent. The electromagnetic field tensor combines E and B into a single frame-independent object. The components change when you change frames, but the tensor itself does not. What about the Earth's magnetic field? The Earth has a magnetic field that shields us from solar radiation and guides compass needles. Does this field really exist? Yes and no. The field is generated by electric currents in Earth's liquid iron outer core. Moving, conducting fluid creates the field through a dynamo process. Those currents are moving charges. The magnetic field they create is ultimately a relativistic effect. An observer moving with the charges would see a different mix of electric and magnetic field. But from our perspective on Earth's surface, the magnetic field is a useful and accurate description. We experience it as a force on compass needles and charged particles. The field is real in the sense that it has measurable effects. It is an illusion in the sense that it is not fundamental. It arises from the relative motion of charges. The lesson Magnetism taught us that apparent complexity can hide underlying simplicity. Two forces become one. Separate phenomena become aspects of a single phenomenon. What seems fundamental turns out to be derived. This is the pattern of physics. Newton unified terrestrial and celestial gravity. Maxwell unified electricity and magnetism. Einstein unified space and time, then mass and energy. The electroweak theory unified electromagnetism and the weak force. Each unification revealed that the universe is simpler than it appears. Different phenomena, previously treated as separate, are recognized as the same thing, viewed from different angles. Magnetism does not exist as an independent force. It is electricity, transformed by relative motion, made visible by the structure of space-time. The next time you pick up a magnet, remember, you are holding a piece of special relativity. The force you feel is Einstein's theory, made tangible. The universe runs on electricity. Everything else is a matter of perspective.